All right, today we're going to unravel the incredible story of how computers evolved. It's this relentless quest for machines that are smaller, faster, and smarter. And the journey from these massive, room-sized giants to the pocket-sized brains we carry around it's absolutely fascinating.
Okay, so let's just dive right in. On one side, you have the pioneers from the 1940s. These were absolute behemoths that filled entire rooms, guzzled insane amounts of power, and were frankly incredibly fragile. And on the other side, well, you've got the sleek, powerful devices we all carry in our pockets every single day.
So the big question is, how on earth did we get from there to here in just a few decades? This isn't just a story about things getting better over time, it's really a story of survival. Each new generation of computers had to solve a critical and often fatal flaw of the one that came before it. So let's start at the very beginning, right? The first generation. This entire era was basically defined by one single piece of technology, a piece that was both totally revolutionary and, as we'll see, deeply flawed.
And here it is, the hero, and maybe the villain of our story, the vacuum tube. At its core, it's really just a controllable switch. Think of it like a tiny little light bulb that you can turn on or off, and by doing that, you either allow electricity to flow or you block it.
And this is just fantastic because it shows the actual birth of binary logic in hardware. You heat up a little filament, use a grid to control the flow, and boom, you get an on state or an off state, a 1 or a 0. That simple physical switch is the foundation for, well, everything that comes next.
But here's the thing. These giants had fatal flaws. You needed thousands of these vacuum tubes all burning hot at the same time. This created scorching heat and used an immense amount of power. And the worst part? They were so unreliable. A single tube burning out could crash the whole system, which meant engineers were basically full-time repair technicians.
So, the solution to this vacuum tube nightmare? Well, it sparked a revolution. The second and third generations were completely defined by a game-changing invention that moved computing out of that fragile world of glass and into what we call the solid-state era.
And here is that giant leap, the transistor. This tiny little switch, made from silicon, did the exact same job as a bulky vacuum tube, but it was better in every single way. No vacuum, no heated filament burning out, just solid, reliable material.
And I mean, just look at the difference here. It was staggering. Transistors were thousands of times smaller, they used a tiny fraction of the power, and they were exponentially more reliable. For the very first time, computers could become both more powerful and a whole lot more manageable. Okay, so with the individual switch problems solved, the brilliant engineers of the third generation looked at this new world of smaller, more reliable computers and asked a really logical question. What if we didn't have to wire all these tiny transistors together by hand? How can we pack them even closer? And their answer was the integrated circuit, or the IC. The real breakthrough was figuring out how to basically print or etch multiple transistors and all their connections directly onto a single piece of silicone. This got rid of miles of wiring, it dramatically shrank the computer, and it kicked off the era of true miniaturization.
And now we are entering the fourth generation. This is where that whole process of integration leads to the single biggest breakthrough in computing history, the one that eventually put a computer on every single desk.
And here it is, the microprocessor. This was the moment when engineers could put all the core parts of a computer, the part that does the math, the part that directs all the traffic, and its short-term memory, all of it, onto one single chip, an entire computer brain on a tiny little square of silicon. This just led to an explosion in density. Using this technique called Very Large-Scale Integration, or VLSI, engineers could suddenly etch millions, and then eventually billions, of transistors onto one chip. We went from a handful of switches to a literal city of them.
And the result of all that incredible density? Well, computers finally became small enough, cheap enough, and powerful enough for you and me to own one. The microprocessor is what ushered in the age of personal computing. The PCs, the laptops, and the smartphones that completely define our world now.
So that brings us to today and the fifth generation. The challenge now is no longer just about raw speed or size. Nope. The new frontier is about making our computers truly intelligent.
The core tech of this fifth generation isn't really a single component. It's a totally new approach: artificial intelligence. Instead of just executing commands we give them, modern systems use what's called massive parallel processing, often using GPUs, to learn from huge amounts of data. And this is what allows them to recognize patterns, make predictions, and even talk with us using natural language.
So, after this whole incredible journey, what's the big takeaway? Well, it turns out there's this really clear, powerful pattern, like an engine of progress, that's been driving this entire evolution.
This table right here tells the whole story at a glance. You see, each generation is defined by its core device. And with every single leap, from vacuum tube to transistor, from IC to microprocessor, computers became exponentially smaller, faster, and way more reliable.
And it all comes down to this simple but incredibly powerful loop. First, a better, smaller switch gets invented. That allows us to pack more and more of them together. That's higher integration. That density leads to smaller devices, which in turn makes them faster and smarter. This cycle right here is the engine of modern computing.
Which leaves us with one last and really fascinating question. We've gone from building computers with fragile glass bulbs to etching billions of transistors onto silicon. But as we start to approach the physical limits of what silicon can do, what's the next great leap going to be? What big problem will the sixth generation have to solve?